So one of you asked the following question about the proof that we did about the self-contained proof of a real and symmetric matrix has a basis of, you get a basis of orthonormal eigenvectors. So in that proof we had something of this form, AR equals RB. What was happening is that R was this tall matrix, K, and then K, and the columns of R were like the, an orthonormal basis, so therefore you have what? R transpose R equals IK, okay? So the argument here was, so what we had is R transpose AR equals B, and then we say, okay, B, well, we left it like this. So from here, what did I say? B was a small k by k matrix. And I argued that, okay, B has an, eigenvalue theta and eigenvector, I forget what we call it, V, okay? So the question that one of your colleagues asked is, okay, how do you know this theta is real, this V is real? Okay, so I guess I didn't mention it in the proof, but you can go back, and so you have AR equals RB. You multiply to the left by R transpose, so you get R transpose AR equals B. And what is this going to tell you about B? It's symmetric. So because B is symmetric and it's real, then you're going to get here that has to be real eigenvalues and eigenvectors. So I just, yeah, that's a very good point. I'm sorry for not mentioning earlier, but that's, yeah, B is a symmetric matrix, so that guarantees real eigenvalue, real eigenvector.
Is the matrix A symmetric?
Yeah, because yes, because this is the stuff that we're doing. We're doing it for real and symmetric matrices. Yeah. So this is I think it was like step 4, where we wanted to show that. It was step 3 where we wanted to show that if you have any A invariant subspace, it contains an eigenvector of the matrix, and we took the A invariant subspace. We take the columns to be a basis, orthonormal basis for that subspace. So because of that because of A invariant, A times R is going to be a linear combination of R's so you get here, you get this. And again, yes, that's a very good point. You need A to be symmetric to guarantee that B is symmetric. So you see, it's useful to go through these proofs to kind of see the key junctions where the assumption about your matrix is used. The fact that symmetric is helpful. Like you saw from the other part, like the approach using short upper triangular theorem, you see there that symmetric plays a role there, because if you're looking at upper triangular matrices that are symmetric, you're forced to be diagonal. Here, this is the place where symmetric is used, that B is guaranteed to be symmetric, real, and so on, and that's your done. Okay, so I just wanted to clarify this before we go. Okay. So again, if you have questions, and if I miss steps or if I skip anything, just write it down. I already got some question about this already. I didn't even go through the proof, but people were asking about converse and so on, so we can talk about that, so on. And if you have questions and comments, you can write them down, and in the afternoon, I'll be more than happy to ask you to come to the blackboard and try to see how it is to lecture 50 students and so on. So we can do that. Okay. All right. So yeah, thank you about catching this thing about lambda 1 greater or equal to lambda n. Okay, so here, gamma connected graph, let's just put something on n greater or equal to 2 vertices. So that, because if I have one vertex, there's the 0 matrix, so lambda 1 will be 0, so we'll just avoid that. Okay? Okay. So again, the part that we did earlier, the fact that we have real and symmetric guarantees that we can order the eigenvalues, the real lambda 1 to lambda n. Now, what tells you that lambda 1 is positive? The simplest proof, lambda 1 is positive. Yes, trace. So, so trace of A, because it's undirected, so because gamma is simple, 0 is the trace of A, which is lambda 1 plus lambda n. Okay. So what does it imply?
It has some positive and negative items.
What?
It has some positive and negative items.
Why can it have all
At least one.
Yes, they're real. And?
Most cases,
Okay, so that's what I'm asking. We're kind of going around the circle and it's all, so why at least one is positive? Oh, you can say, well, because at least one is negative. Okay, and then why is that? You cannot go again because one is positive, because there cannot be all.
All cannot be negative or cannot be positive.
Clearly, yeah, all cannot be, yeah. All cannot be positive, all cannot be negative, but all cannot be zero. Why all cannot be zero? Because the graph will be 0, 1. Okay, so because gamma is connected, so not all eigenvalues can be 0, and so you'll have some positive and you'll have, well, you'll have something non-zero. And why can't you have lambda 1 be 0 and everything else? Huh? Negative.
The sum should be 0, so that implies everything.
Sum is 0. Yes, there you go. Okay. So from here, figure out the details. Lambda 1 is going to be positive. Okay. You will see it will come up from something like this about the eigenspace is spanned by an eigenvector. So let's try first. I want to convince you that you can find there is an so claim there is an eigenvector corresponding to lambda 1 that has okay. So there are several ways to do this. Again, after we go through some of these ideas of this proof, we're going to state the one for general matrices, like irreducible matrices, where these things will be true plus some extra stuff. Now, for this proof, what do we have? We have a u1 equals lambda 1 u1 for some u1, which is real, which is not 0. And so what guarantees that we have an eigenvector? The first theorem that we did in class, that it's real symmetric, you have an, but spectral decomposition, you're going to have an eigenvector here. How do we go about, because I mean, if you just say any eigenvector will have this property, it's not going to be true. It's not true that every eigenvector here has positive entries. So if somebody wakes you up at night and says, okay, here's my matrix, here's my eigenvalue, where do we go to find an eigenvector that's going to be positive? Okay, so I'll give you a couple of proofs of this statement. So let's see. Now, here you see this will come up because we'll talk about Rayleigh quotients and so on. Whenever you have A U1 equals lambda U1, you multiply to the left by U1 transpose, and you're going to get something like this. Okay, you multiply to the left. And now, maybe we want to make our life easier. So let's take, if I have an eigenvector, I can always divide it by its norm, and I can normalize, I can make it of length 1, and that way, so I can say here U1 transpose U1, which is the length of U1 is 1, and in that case, you get your lambda 1 just here. Okay? All right. So lambda 1 is going to be U1 transpose A U1, and you can expand this, and this is going to be a summation x, y in V of A x, y U1x times U1y. So this is an example of this Rayleigh quotient of a matrix associated to some vector. Okay. And now, so what I want is I just picked one eigenvector, and I want to make some kind of eigenvector that has all the entries positive. Okay. So I might as well, let's just define V1. V1 of x is going to be the absolute value of U1 of x. Okay. So what I'm doing is, okay, if this U1 had let's say positive, negative eigenvalues and so on, I just bring them everything on one side. Obviously, you have to worry about, okay, what happens if I had 0? That's where we have to deal with. Okay. Now, before we do this, here's the first. Okay, I'll leave this here. Claim I'll. Here's the first, this place where this Rayleigh quotient will make an appearance. So this Rayleigh quotient is going to be Rayleigh quotient of a vector with an a matrix. So, and it's going to be something, let me call it RAU. I will just use this notation at the beginning now. Maybe I have U there, so let me use W. This is going to be W transpose A W, W transpose W. And this is defined for the matrix A and this vector which is not 0 vector. Okay. Okay. And now in course of our one thing that we will use is that lambda 1, the largest eigenvalue, is going to be the maximum over all W non-zero of this Rayleigh quotient, W transpose A W divided by W transpose W. And if you normalize W, you can just take W of norm 1, so it's maximum overall, I don't know, let me call it V, such that the length of V is 1 of V transpose A. Okay. So this is a claim that you take this this expression, this one or this one, and you maximize over all possible vectors. here all non-zero vectors, here all vectors of length 1, the maximum will always be, yeah, okay. So this is a bit the simplest case of this type of max-min inequalities about Rayleigh quotients and eigenvalues. And let's go to, do you guys all know this, or should I go through it? Go through it? Okay, okay. Let's go through the proof. Okay. Okay, so there are two things. The fact that here it's max, you have to be careful sometimes. In order, if it's maximum, it means it has to be attained. So okay, because otherwise you put supremum if it's not attained. So in order to prove this, we're going to show two things. So we're going to show thing one. We'll show that for any w in Rn, w less than or equal to 0, lambda 1 is greater or equal than okay, so lambda 1 wins all the time. And second, that there exists some vector w in Rn, w is not 0, such that lambda 1 equals okay. Sorry, I kind of got stuck in the middle of this proof and I realized I need this claim. So I'll just do it here. Okay. Okay. I'll erase here and I'll come back to this in a second. Okay. So proof of one, proof inside a proof. And here, this is the place where you use this spectral decomposition. So if you take W in Rn, now I didn't mention, but my matrix A is going to have eigenvalues lambda 1, lambda 2, lambda n, and I can take a basis. So I'll fix myself a basis. I'll pick an eigenvalue for each of them such that this is orthonormal basis for Rn. And these are eigenvectors. All of them are eigenvectors. U1 corresponding to lambda 1, U2 to lambda 2. Okay? So if you have W here, then W is going to be alpha 1 U1 plus alpha n UN for some reals, and because W is non-zero, not all of them cannot be 0. Not all 0. Okay? And then the reason these expressions come into play here is that they play well with orthonormal basis. Everything works out very nicely. So for example, okay, we're going to do the two computation. W transpose W, this is so alpha 1 plus alpha n transpose times alpha 1 plus alpha n UN. And when these vectors from here meet these vectors from here, only the ones that have the same index survive, and you'll have alpha 1 length of U1 square plus alpha, so alpha 1 square, alpha n square. But all these lengths, that's why you take unitary, because it makes your life easier here. So it's going to be alpha 1 square plus alpha n square. Okay? And this is going to be positive because not all of them are 0. Okay. And then the other calculation is W transpose AW. But let me do first AW is going to be A times alpha 1 U1 plus alpha n UN. And then it's alpha 1 A1 AU1 plus alpha n AUN. So alpha 1 lambda 1 U1 plus alpha n, lambda n, un. So A just contracts or deletes the vector by a little bit, and then it behaves nicely when we multiply this to the left by W transpose. So you're going to have alpha 1 U1 transpose plus alpha n UN transpose lambda 1 alpha 1 U1 plus lambda n alpha n UN. And it's almost the same. It's almost the same as here, but you have the lambda ones in there. The same thing happens orthonormal. They kind of cancel each other, so you're going to have what? Lambda 1 alpha 1 square plus lambda n alpha n square. Okay, so all this work to give us what? To give us that W transpose AW divided by W transpose equals, on the top we have this, and now, I mean, if you look at this expression, this is a convex combination of the lambda 1, lambda n, because you can write in many ways. Let me, alpha 1 squared divided by the sum of all the alpha j square lambda 1 plus alpha 2 square divided by the sum of all j equals 1 of alpha j square lambda 2 plus alpha n square divided by the sum from j equals 1 to n of alpha j square lambda n. Okay. And the thing that I wanted to show is that lambda 1 wins, so you don't need this expression. I just wrote it so that you can remember it, but you can go here and you look here, lambda 1, lambda 2, lambda n, which one is the lambda 1? So then you're going to have less than or equal than lambda 1. So okay, so it's useful to do this calculation. Sometimes this is quite common, and like I said, we'll see it in the max-min theorems and so on. Sometimes the W may not. Sometimes you may know that W comes from a smaller subspace, and it's generated maybe by the first k eigenvectors from here, or from the last k eigenvectors from there. So you can play the same game, and you can always know. You will always know where the maximum and the minimum lies of this expression. It's like the largest of your eigenvalues, the smallest, and so on. Okay, so it's the same trick. Okay, so this proves 1, and for 2, it's very easy. You just take, so for the proof of 2, you take W to be U1, the eigenvector of lambda 1. So then A U1 equals lambda 1 U1 implies that what we wanted, that W1 transpose A W1 equals lambda 1 U1 transpose U1. So that's, and because U1 is not 0, you can divide. Okay. All right, so that's okay. That's the claim. Okay, I'll erase the proof. Okay. So let's come back to the Perron-Frobenius stuff. So I have a U1, so I have A U1 equals lambda 1 U1. Let me put this. Okay. And like I said, I can take, let me take U1 to be of length 1. So then I do the same calculation as before, and I have that lambda 1 is U1 transpose A U1, so it's the sum over xy in V AXY U1X U1Y. Okay. So now I want to make a positive eigenvector. So I'm going to define V1 in Rn with V1 of x to be the absolute value of U1 of x. So far I don't know, I could have 0, so I can say greater or equal to 0. And again, because U1 has length 1, U1 is not 0, it's guaranteed that V1 is going to have at least one positive entry, okay? Cannot be all 0, okay? Now, the first thing you do is you calculate this V1 transpose A V1. And it's the same expression there, but now, by the second part here, this is a maximum. I'm sorry for using the same letters V's. And I have V1, this is V. So this is a maximum over all vectors of length 1. I didn't do the calculation here, but you know how to do it. This is, what's the relation between this V1 transpose A V1 and lambda 1? Which one wins? Which one is bigger? Lambda 1. So lambda 1 is greater or equal than that. This is this, which is summation over all xy in V of A xy, absolute value of U1x, absolute value of U1y. How is this compared to this? Forgive me for using this. This is greater or equal than this. Okay, so lambda 1 greater or equal than this is this, greater or equal than this comes back to lambda 1. Huh? So they must be equal, very good. What else? Then V1 is? Can we say, because so V1 so V1 is guaranteed to be greater or equal to 0. So when I write, okay, is guaranteed, all the entries are greater or equal to 0, there's at least one that is positive, guaranteed. But yeah, so you have to place, some of them could be 0. But before we get to that, lambda 1, because of all these equalities, what can you say about V1 and lambda 1? Eigenvector. V1 is an eigenvector. For lambda 1. Okay, so now let's say this is my graph. Okay, you have the graph, it's connected. And now we kind of picked this one because we thought that this is going to be the one that's going to be positive. So you have to play kind of devil's advocate, which is figure out what happens. Okay, let's say here, let's put our money on something. Let's make a claim. For every x in V, V1x is positive. Okay, so let's see. Now, like I said before, because U1 is non-zero vector, V1 is guaranteed to have some positive entries, but it may have some 0. So what you can have plus, 0, 0, I don't know, plus 0, plus, I don't know. It may not even be right, okay? But pretty much you're guaranteed, so let me do another picture here. You're guaranteed that you can split it. If that's the case, you can have all the pluses on one side and you will have the zeros on one side. Because the graph is connected. I mean, this doesn't use the fact that it's connected. I'm going to use it now. But so what I want to show that everywhere it's plus, 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 plus. There's no 0. you can assume there are some zeros. Because the graph is connected, what's guaranteed between the plus and the zeros? There are several characterizations of connected graphs. A graph is connected, what's the definition? Between any two vertices, there is a path between them, but there is another one in terms of partitions. For any partition,
Number of edges from one side to the other side is non-zero.
yes, there is at least one edge from the positive side to this side. So there's going to be an edge like this. Okay? So let's see what happens in that case. So let me just write down what we talked about. So the entries of V1 are non-negative, and there is at least one positive entry in V1. Okay? Now, by contradiction, assume that V1 has some zero entries. Okay? And now we say because now the connectivity, because so far we haven't used connectivity anywhere. Like there hasn't been anything about connectivity. It was just about symmetric matrix. Because gamma is connected, there is an edge, let me call it AB of gamma, such that V1 hat of A is positive and V1 of B is 0. Like this would be the edge, like there is an edge from the positive side over there. Okay? So now, it's a proof by contradiction, so we need to find something wrong. We need to find a problem. So for this one, you go, V1 is an eigenvector. So because it's an eigenvector, you have AV1 equals lambda 1 V1. And then you specialize it on, look at this at the B entry. So you got, let me write it this way, lambda 1 V1 in the position B, let's say B, equals the AV1 in the position B. Lambda 1 V1 in B, so this means lambda 1 V1 B, which is 0, is going to be what? It's going to be AV1 in B. AV1 in B, it's a sum over what? Over all, let's say, C adjacent to B, I'll write it like this, of V1C. So I'm writing this a bit faster. Maybe, let me do it in one, before I do this, let me do it like this. So AV1, it's the matrix A multiplied by V1, so it's the sum, let's say, over all Z in V of A, what is it? A, B, Z, V1Z. You take the row, the B row of A, and you multiply it with the vector V1. But A is a 0, 1 matrix. So the only ones that survive in this sum, the only Z's that survive, are going to be the Z's where A, B, Z is 1, and those are the ones that are adjacent to B. So your B, you're going to be here, you have A, but they could be more. So this is going to be summation over all Z adjacent to B of V1Z. Okay. So what do you know about these entries? All of them are greater or equal to 0, and there is one that is positive. So this is greater or equal than v1a, which is positive. And so that's a contradiction. And that's that. Okay. Yes, yes.
So, to prove V1 transpose A V1 equals lambda, implies V1 is an eigenvector of lambda 1, we need an argument, right? Is that meaning?
Well, here we see like, so U1, I erased it here. U1 is of length 1. That means that V1 will have length 1. And then here, what did we prove? All this argument, lambda 1 greater or equal to this is because lambda 1 is the maximum, equals this, greater or equal to this, ended up at lambda 1. So you have to have equalities everywhere. Very good point. And now, he's asking a very good question. So where are we with exercises? Oh, you can thank your colleague for more exercises. X6 one. Okay. So exercise 6. Exactly here you have V1 in Rn. Norm of V1 is 1. And you have that lambda 1 equals V1 transpose A V1. This implies V1 is an eigenvector. The proof is the same. Again, the spectral decomposition, you always, because you take this V1, you write it down as a linear combination of, now you have to have a different notation because you need to separate your eigenvalues into distinct eigenvalues. Lambda 1 is the largest, then you write down the distinct ones. And this V1 is going to have a component for each of these kind of eigenvectors. But because of this equation here, from the spectral decomposition, you will get that V1 is just a linear combination of the vectors that correspond to lambda 1. So V1, but you have to write it. I'm not going to write it, but so exercise 6, okay? Yeah, so that's the key here because you want, yeah, that's what I used here. Yeah. So that exercise has a little bit of a converse. It's, you have, when you plug in the eigenvector into the Rayleigh quotient, you get the eigenvalue for the largest eigenvalue. If a Rayleigh quotient gives you the largest eigenvalue, that eigenvector has to be that vector has to be an eigenvector. That's all. Okay. 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 So we did this. Let me see if I give you a different proof. Okay. Let me give you a slightly different proof of this result. I'll just give you the sketch. So this one is kind of dealing directly with these eigenvectors and zeros and positive and so on. Let me give you a slightly different proof. I'll just erase here. So maybe second proof, positivity of U1. Okay. So now the same thing as before. You see, like this argument, you take an eigenvector, you take the absolute value, you get something greater or equal to 0. But now, so let's say I have again a V1 equals lambda 1 v1, v1 greater or equal to 0, and let's assume length of this is 1. So over there, we just gave an argument that v1 has to be positive by doing this eigenvalue eigenvector equation. You can do it in a different way. You can prove that v1 is positive, and this is kind of related to the matrices that are used in a little bit in the proof of the Perron-Frobenius in general. So you can take as a matrix the following matrix. You can take something like I plus a squared plus a and minus 1. I'll tell you in a second why you can take this matrix, or you can take you have more choices than a matrix here. Now, what's so special about this matrix? Because again, gamma is connected, and there's something that I haven't proved yet, that the entries of the powers of A count the number of walks between vertices in the graph. So gamma is connected, you're guaranteed that A is a 0-1 matrix, but when you take all these powers all the way to n minus 1 and you add them up, what are you guaranteed about M? Everything is positive. So all the entries of M are positive. Okay? Now, this is not the only choice, and again, here's exercise 7. Gamma connected if and only if this matrix I plus A has positive entries. Okay. You can take this, or you can take, if you don't like this matrix, you can also take I plus A to the n minus 1. Essentially, any linear combination of I, A squared, A minus 1 with positive coefficients is gonna do it, okay? Because of this business of counting the walks. Okay, so one thing is M are positive, but there's something else, because you wanna get to V1. So A V1 is lambda 1 V1, so V1 is also an eigenvector for M. Yeah, so from here, you're gonna get M V1 is gonna be something, okay, 1 plus lambda 1 plus lambda 1 n minus 1 times V1. Okay? So now, you can give, from here, you can give another proof that all the entries of V1 are positive, again by contradiction. V1 is greater or equal to 0. So assume that you have an entry that is going to be 0. You look at, so essentially you pick up that entry from your vector V1, and you look at this equation at that entry. And so on one side you're going to get 0. On the other side, what are you going to get? Well, if this entry is 0, my vector V1 cannot be the 0 vector, so there's something outside of it that is non-zero, and it's going to meet an entry from M, which is also positive, and is gonna burst into flames and go. So that's the proof. That's a different proof of this. Okay. Okay. All right. Let me erase here. Okay. Okay, so what did we do? We did this. We did that we have a positive eigenvector. We didn't do the multiplicity. Yeah. Here again? Okay. So here, this entry, this M is all positive entries. Okay. This is also positive. Okay. So now what do you want to show? You want to show V1 is already greater or equal to 0. So you want to show that, so from here, let me put it here, claim, again, for any x in V, V1x is positive. Okay? So the proof is again by contradiction. So assume there is, I don't know, some vertex, I'm gonna give it a different name, A, no, I use A, B, C, I'll use D, I don't wanna do Y in V such that V1Y is 0. Okay? Now here I have M V1 times something positive, let's call it f of lambda 1 times V1. So now we look at the entry y in both of these places. So you look at what is f lambda 1 V1 in the position y is equals mv1 in the position y. Now here, you know what you're gonna find. You're gonna find f lambda 1 times v1y, which is 0. Now what am I gonna find here? Now here, M is not a adjacency matrix. It has like, all the entries are positive, so they're gonna be bigger than 1, but you write it down. It's a summation of what? Over all z, z in v, m, y, z, v1z. Okay? Now, every one of these entries is positive. But now v1 is not a 0 vector. And v1 is also greater or equal to 0. So there's going to be one of these z's, not all, at the end all of them are positive, but at this point you only know that one of them is positive, at least one of them. So at least one z has v1 of z positive. So you see the game is fairly simple. You move from A because A works in your favor, but you have 0 entries, and the 0 entries mess up your thing. So then you move from A. How can I make from A a matrix which has all positive entries? And like I said, this is one way, or this is another way, or you can take, there are many ways. But you take an M, which has positive entries, that's going to have the same eigenvectors as A. And then you get to here. Does it make sense? Is it clear? Yeah, perfect. Thank you. Okay. Okay, second proof. Let me erase here. Okay. So we can add it to exercise 7. I don't want to make exercise 8. Just put it here. If and only if I plus A has positive entries. And now think about if this n minus 1 can be reduced to another number. Okay. That depends on the graph. Okay. So. Okay. Okay, so let's do this one first, and then we can do this one. So let's prove. Or let me see, which one do I want to do next? Okay. Yeah, let's do this one because it's easier. This one. So let me prove that absolute value of lambda n is less than or equal than lambda 1. Claim. Okay. Again, it helps to think of lambda 1 as an eigenvalue, but to think about it as this kind of optimum of this Rayleigh quotient business. Because if you think about that, then things kind of orient in the right way, and you have lambda 1 greater or equal than something. So earlier we saw here that lambda 1 was the maximum of all Rayleigh quotients and all that stuff. So lambda 1 beats all the Rayleigh quotient. So maybe you will beat something that involves this. So that's kind of the idea. So proof. So you take un in Rn, un not 0. Well, un, let's say, of length 1 as before, such that lambda n, a times un equals lambda n times un. And as before, therefore, un transpose a un equals lambda n. So you got your hands on lambda n from here. Okay? Now, what do you want here? You want absolute value. So take absolute value. So you have absolute value of lambda n is absolute value of un transpose a un. And this is going to be absolute value summation over all xy in V, a xy unx uny. And then use triangle inequality is going to be less than or equal than the summation over all xy in V of a xy unx uny. Yeah. Now, if the vector un has length 1, if I replace all the entries in the vector un by their absolute values, that vector also going to have length 1. So from here, if I take the absolute value of this vector un, the length of it is also going to be 1. Okay? If you square the number or square the absolute value, it's the same thing. So here, what do you have here? Here, this is a Rayleigh quotient. This is the same thing as this vector un. Let me write it like this. A transpose. So I'm sorry for the notation. I'm introducing notation here. This notation is the vector where all the entries are the absolute values of the un. But what do you know about the Rayleigh quotient of any vector of length 1? Who is the boss of all of them? Who beats all of them? Lambda 1. So that's it. So that's that. Okay. Okay, so let's do now the multiplicity business. Where do I have it here? Okay, so we're gonna follow the same script. So claim not strictly lambda 1. Okay, so we'll follow the same script from here. So because again, you see, like the way you can guide sometimes, you see which side is lambda 1. Lambda 1 is the side that is greater or equal. So it kind of, okay, maybe I use this thing about lambda 1 being the maximum of all these Rayleigh quotients. So again, consider, let's say, u2 in Rn. Norm of u2 is 1, such that a u2 equals lambda to u2. Okay, and we do the same type of argument. Therefore, lambda 2 is going to be u2 transpose a u2. And let me see if I need absolute value. Yeah, so I'll take again v2. So define v2 in Rn by v2 of x equals the absolute value of u2x for x in Rn. And then, okay, so we'll do this. Lambda 2 is this. Now this is going to be the sum over all xy in V, axy, u2x, u2y. And now we're going to say less than or equal than the summation over all xy in V of axy, absolute value of u2x, absolute value of u2y, which is the Rayleigh quotient of V2 transpose A V2. And that's going to be less than or equal than lambda 1. Okay. So it almost works. So you have lambda 2, this, from here. Then this is algebra. Less than or equal because absolute value beats the number. This is of another vector, which is less than or equal to lambda 1. But the thing is, what do we want somewhere here? You want some strict inequality. So let's see, how do we find a strict inequality? Well, there's another thing that we haven't, okay. What can we assume about, so, okay, these vectors u1, u2, un are what? Orthonormal. So one thing we haven't used about u1 and u2. They're perpendicular on each other. So you know for sure, we know that u1 is positive. We can take u1 to be a positive eigenvector, and u2 is going to be perpendicular to it. So u2 is guaranteed to have what? Negative and positive, and you could have zeros, okay? So here, let me, the proof goes by two cases. So case 1, let's say u2x is not 0 for any x in V. So if u2x is not 0 for any x in V, it means that if you take your graph and you split it according to the entries in u2, you're going to have again pluses and minuses, because this fact is because u2 is perpendicular on u1. u1 is positive, so it's going to be a linear combination of the entries in u2 is going to be 0. u2 is not 0, so you will have positive or negative, and once you have positive, you're going to be forced to have negative by this condition. And because this assumption that, let's say, none of the entries are 0, it's going to be split in positive and negative. Then where can I find some strict inequality here? You can find a strict inequality here because, again, what are you going to use? The graph being connected it means that there's going to be some kind of edge here that goes from positive to negative. There is some edge AB, where the entry here is positive, the entry here is negative. So if you look here, U2A times U2B, so A is positive, B is negative, so this is going to be negative, and then this is going to be strictly less than absolute value of U2A, U2B. Make sense? Huh? Well, so this is a case where there are no zeros. So the case where there are no zeros, you separate into positive and negative, and we kind of did this before. And again, you see the place where gamma being connected plays a part. There is a place where you have something positive, something negative, and then this will guarantee you here that it's going to be, you will have a strict inequality, okay? So that's this part. Okay, so obviously case one is the easier one, but you know, not everything in life is easy like case one. So you have also case two. U2 So there is a possibility that this U2 of x may be 0. Okay, why is this one happen? It cannot be happen at the same time as with equality throughout. That's what you're saying. Because again, the game is we want to show that there's strict inequality here or here. If you have inequalities, so first, if you have equality here, what does it tell you about B2? It's an eigenvector of? Yeah, and then there is something there. So where are we with exercises?
7.
Okay, exercise 8, finish here. Finish the proof here, okay? Okay. Okay. Okay, so now let's do something about spectral graph theory. So let's do a theorem. So let gamma be a graph with adjacency matrix X1. So this will be one of the first results where you will see this connection between combinatorial properties on one side and eigenvalue properties on the other side. And it's probably familiar to most of you, but let's do it. If gamma is bipartite, then the spectrum, which I haven't said what it is, but I'll mention in a second. So the collection of all the eigenvalues of A is symmetric with respect to 0. So what do I mean by this? I mean, if let me say, if lambda is an eigenvalue of A with multiplicity M, then minus lambda is an eigenvalue of A with multiplicity M. So I haven't talked about multiplicities, you know, as you know from linear algebra, there's geometric multiplicity, algebraic multiplicity. Here, because everything is symmetric, they are the same. So here, yeah. So that's what I mean by the spectrum being symmetric with respect to 0. Now, there are two converses to this theorem. So the first one is just you do the converse from here, okay, like just the other way around. If the spectrum of A to 0, then gamma is bipartite. I assume everybody knows what bipartite is, but I'll give the definition in a second. Now, third is actually the stronger result of a converse, but it only applies if the graph is connected. So if gamma is connected with eigenvalues lambda 1 greater or equal to lambda n, and so in the case that gamma is connected, to guarantee bipartite, I don't need this strong hypothesis that all the spectrum is symmetric with respect to 0. I just need the condition about lambda 1 and lambda n. So earlier, what did we saw? We saw that lambda 1 beats lambda n in absolute value, so it's going to be greater or equal than minus lambda n. Well, if gamma is connected with eigenvalue this, and lambda 1 equals minus lambda n, or you can say it the other way, lambda n equals minus lambda 1, or lambda n equals minus lambda 1, then gamma is bipartite. But you see, you have to be careful when you apply these results, because here, gamma is anything. Here for 3, you need to use this. It's correct. So again, let me recap. So you have a graph, gamma, with adjacency matrix A. If the graph is bipartite, then the spectrum of A is symmetric with respect to 0. What you see on the positive side, you're going to see on the negative side with exactly the same. Obviously, the negative of 0 is 0, so over there you see something. Doesn't mean that multiplicity of 0 has to be even. It can be any number. Now, conversely, if the spectrum is symmetric with respect to 0, then the graph is bipartite. And if you apply this to graph connected with these eigenvalues, then you only need to look at this. You don't need to check the whole spectrum. If these two are negative of each other, then gamma is bipartite. Okay. So again, this is a lucky. I mean, it's a lucky occurrence where you see this, in some sense, equivalence between the combinatorial property and something about linear algebra about the matrices. So let's go over the proof. Okay. Okay. So let me tell you first. Okay. Definition. What do I mean by bipartite? So just to avoid like trivialities, bipartite will have a graph that has at least one edge. Okay. Empty graph. Yeah. If is bipartite if gamma has at least one edge and there is a partition of V equals S T such that any edge of V has one endpoint in S and the other and another endpoint in T. Okay, so the picture will be like you have I don't know, something like this. So you have two subsets of the vertex set. These are all your vertices, and no edges inside S, no edges inside T is bipartite. And so you have this characterization, combinatorial characterization. So proposition a graph is bipartite if and only if it has no odd cycles. So if you want to check bipartiteness, that's very easy. You can do like this search, this traversal of the graph called breadth first search, and you can check that you have no odd cycles. So you kind of, you start at the vertex, you list the neighbors, and then do I have any edges here? If you have an edge here, you have a triangle, you're not bipartite. So okay, but if you don't have any edges, you continue. You look at the different thing. If you see an edge here, that means you're going to have an odd cycle or odd 5 cycle, and you're not bipartite. And you continue like this until you traverse the whole graph, and then depending on your answer, you decide if your graph is bipartite or not. You need like this. You need these kind of neighborhoods to be all empty in order to be bipartite. Make sense? Yeah. Now, again, the reason why people like many problems in graph theory are hard. So, chromatic number, independence number, all this stuff. Some of these, many questions, when you look at them at bipartite graphs, you have like, you're lucky. They're easier to solve in that case. So bipartite graphs are easy, and they're also the same graphs where the chromatic number of the graph is 2. You can color the vertices with 2 colors, such that you give these vertices one color, these vertices one color. Every edge has different colors on the endpoints. Okay. Okay, so let me erase here. Okay, so proof 1. Now, let's take gamma, let gamma be a bipartite graph. Now, I don't know, depending on which book you read, S and T here sometimes are called partite sets, or sometimes are called color classes. And this is just for bipartite graphs, because color classes, like I said, is because you can color here with one color here with the second color. A bipartite graph, it's a specific case of a multipartite graph in which you have more parts, so that's why it's called partite sets. So a bipartite graph with partite sets S and T. So this is your graph S and T here. And now we haven't gone to it, but we're going to talk about it in the tutorial. In the definition I gave of adjacency matrix, I call it the adjacency matrix. And I said you have a label, you start with the vertex set, and you have these vertices in V, and I label them 1, 2, 3, 4. Obviously, you can ask yourself, well, what happens if I don't like 1, 2, 3, 4, the ordering, and I want to do 4, 3, 2, 1, or any other ordering? That is an adjacency matrix. So you have as many adjacency matrices as you're going to have possible ordering of your vertices, and you will have different adjacency matrices. They will look different than the one that I have. But we'll see in the afternoon in the tutorials, all these adjacency matrices will be similar to each other by a permutation matrix. So all of them will have the same eigenvalues. So when you talk about eigenvalues, I can just say I take one ordering of the vertices and I will pick the adjacency matrix corresponding to the ordering because it helps me in a certain way. So that's what I'm going to do here, because I want to do an ordering of the, like a way of adjacency matrix. So I will have a way to label the vertices of the adjacency matrix such that A of gamma is the following. So I want to put first the vertices in S, followed by the vertices in T. Okay, and the reason I do that is because in S, I know what happens. In S, there are no edges. So here I will have a 0, and let's just say cardinality of S is S. So this is 0S. This is the S by S 0 matrix. And here I will have another 0, which is 0 by T, where cardinality of T is T. Now you can ask yourself, okay, what are you going to have here? Something. Okay, how do you want to call it? B. Why not? B. If B is here, what is here? Very good. Is B square or not square? S cross T. It may not be square. It may not be square. We don't care. Okay, so that's how it looks like. Okay, so now let's see what happens if lambda is an eigenvalue. So let's take lambda positive. Then we're going to have A times some vector u. It's going to be lambda times some vector u. Okay. Now u is as big as the matrix, and the matrix already we see that is kind of split into these blocks. So that makes it clear for us that we should split our u. We look at our vector u as something v on the first part, something w here. These are the first S entries, these are the T entries. So you kind of go a bit more into this equation based on the way your matrix looks like. So it makes sense to write it like this with v and w. And so then let's write this. We will have, let me write it here. So we have A u equals lambda u. A is of this form, 0s 0t b b transpose is going to meet v and w, and is going to equal lambda v and w. So you have it like this. So this equation is going to be equivalent to what? And now you go in and you do the calculation. 0sp meets vw, so you get bw is going to equal lambda v, and the second one, b transpose v, will equal lambda w. So everything in here is in here. I just did the calculation. All right. And now you pick at what do I want to show? If I have an eigenvalue, I can have a negative eigenvalue. So you try to, I have one eigenvector. Now I can try to guess an eigenvector for minus lambda. Okay. I'm going to erase here. So define, what do we have? We have u, v, w. Okay, what's a good name for vector? After you use UVW, what are you going to use for a vector? Huh? We use X for vertices. Let's call it U1. And no, not U1. UN. Define UN because it's for the small. Not UN. U prime. No, because it's U prime. Define U prime in Rn. U prime is, I keep the V from the top, I take the negative W here. Okay. So now, one more thing. Okay. AU is lambda U. U has to be non-zero. So if U is non-zero, what can I say about V and W? At least one of them is non-zero, but then you go, okay, lambda is positive. Let me see, how do we get, okay, for now I don't need, so at least one of them is non-zero. So it implies V not zero or W not zero. So because of that, this vector is guaranteed to not to be zero. Okay, and then you hope something works. Okay, when you multiply, so you have AU prime 0s 0t b transpose, and you multiply it by v hat minus w hat, and what we're going to get, 0s here, it's going to be minus bwv. B transpose here is going to be B transpose V. How much was BW? Was lambda V. Minus lambda V now, thank you. B transpose V is lambda W. And now we started with V minus. Here we have minus plus, so you put minus lambda V hat minus V hat. So that proves that this is not zero. This equation proves that minus lambda is eigenvalue. So that's very, very nice. But I have something more there. I have a stuff about multiplicity. So it's not just, okay, for sure lambda is an eigenvalue, minus lambda is an eigenvalue, but now why is minus lambda have the same multiplicity? So where are we? Yes, but exercises. Exercise 9, okay. Let's say I have, I'll use, so what, okay, I have V1, W1, I have VM, WM. Let's say this is a basis for the eigenspace of lambda. Let me just call it E lambda, or let's say fancy E lambda. So you know fancy E lambda? LaTeX, math, \math cal. Okay, so \math cal of lambda. So if this is a basis, what I want you to show is that V1 minus W1, VM minus WM are going to be linearly independent. At the end, they're going to be a basis, but for now, in the first step, just prove that they're linearly independent. I mean, here, it's not about basis, it's about linearly independent. Because these vectors are linearly independent, show that these vectors are linearly independent. And so how is that going to help me with multiplicity? So I'll just say this and then we finish. If this is a basis, M is the multiplicity of lambda. if we prove this exercise, this is going to be linearly independent, and these are eigenvectors for minus lambda. So this guarantees that multiplicity of minus lambda is at least m, okay? But then you can play the same game backwards with minus lambda and lambda, so you get that the multiplicity are the same. But this is what you need here to prove that from this linearly independent, these are also linear. I mean, at the end, like I said, these imply basis, but for now, just linearly independent. Okay, we'll stop here. Thank you.